Hey everyone, this is Tomer Levi, and I'm a data engineer with Funbox. I'm from Israel, and in my session I'll show you how we build our unique data platform using serverless technologies on AWS. And I think that Chelsea FC is going to win the next Premier League season. Hello, thank you for joining my session today. My name is Tomer, and I'm from Funbox in Tel Aviv, Israel. And today I would like to share with you our road to achieving and orchestrating a data platform using serverless technologies. The session will be a technical session. I will try to share some code examples along with the architecture layouts. I'm assuming that you familiar a bit with coding and familiar a bit with cloud infrastructure and so on. Not very deeply, but you need to have some kind of understanding of those concepts. And let's start. So a bit about me. I'm a senior data engineer here with Funbox. I really mad about technology, especially things around data, machine learning, and serverless and cloud computing. And I'm also a sports fan. I really like Federer, and I hope he's going to win another Grand Slam soon before he retires. And Chelsea FC is my team, as you saw in the pre-session video. And I really think they have a chance to win the Premier League, but don't take me for granted. So 2 words about Funbox. I'm promising you that after that, we're going directly to the interesting stuff. Funbox is a fintech company, and the problem we're trying to solve is to help our customers with credit lines, with loans, basically. So let's say I'm a pizzeria owner in the United States, and I want to get a loan for my business. Usually I would go to my bank and I would ask the bank to give me a loan. This process is going to be, I don't know, not very efficient, at least. It's going to take around 2 days. They're going to ask me a lot of things which I need to provide, a lot of reports, and they're going to look at my personal credit score and credit information in order to give me a loan, okay? Eventually, this kind of process is also expensive, and these expenses are rolled into my interest rates, and I'm not, and I wouldn't get the results faster enough. This is why we in Funbox, we are doing something different than the traditional institutes loan. We use automatic processes and machine learning models to estimate the risk potential customer possesses on our business, and using an automatic process with nobody involved inside, we can lower the cost, we can get a much higher approval rate, and we can get a comprehensive view of the customer and the business because we're using external data sources, and by that we achieve a more comprehensive view of the business. Last year, we were nominated by Forbes to be one of the most promising AI companies in Americas, and we are located in 3 locations. San Francisco is the headquarters, Tel Aviv is the R&D, and Dallas is the customer front representatives. Now, we define ourselves as a data company, and like many other data startups, there are multiple data, I would say, users, okay, or stakeholders. Data analysts, they want to use the data to create reports. Data engineers, they want to write their ETLs. Yes, we like ETLs, and I told you we are fetching data from multiple data sources around the globe to understand how business behave. So we do that along with the feature engineering to help our data scientists. And data scientists, they want to explore the data, they want to prepare the data for training and to train their models. So all of these stakeholders want to interact with the company's data somehow. Now, let's imagine that I'm this data analyst and I wrote a daily report SQL file. And I want this report to run every day at 6 a.m. Just before people are opening their laptop in the morning. I want the report to be available for them. So I created this wonderful piece of Python code, which reads the SQL query. It creates a connection to our data warehouse, of course, providing username and password hard-coded in the code. And after the results fetched, I'm logging the results into the output, and this is all I want to do. Now, prior to the platform we developed as a data analyst, I would stand with my piece of code inside my laptop, and I want to run this job every day. Of course, I need to find some backend server to do that job for me. So I would SSH into one of the many EC2 servers out there in the cloud. I would upload my Python code and hope for the best. Yeah, I probably need to tune some cron expressions to kick in at 6 a.m. exactly. But then what if something breaks? What if something is not working as expected? How can I understand what happens to my code? I have no monitoring. I cannot collect logs. I have no alerting system in place to notify me that something bad happens. And if I'm using a relatively small piece of code, that might be easy for me. But what if I write a report which contains many files and dependencies and so on? This is going to be a nightmare for me. So that's exactly why we created the platform. The platform allows those stakeholders in the company, the data stakeholders, to focus on their main inquiry on the business rather than taking care of infrastructure and understanding what we need to do in terms of technicalities. Take your code, take your SQL code, take your Python code, take your business logic and execute it without worrying about anything else. So in addition to the simplicity, we wanted to have additional things with the platform. First, we wanted to scale the platform to hundreds of jobs. As you can see in the previous slide here, it was not very scalable because let's say I have 3 backend services. What happens if I have more jobs than resources? It's a kind of a bottleneck. So with the new platform, we wanted to scale to hundreds of jobs a day, or maybe thousands of jobs a day. We wanted to support both or any language from Python to SQL to Spark to Go to whatever the user choose to use. And of course, we wanted to use different kind of infrastructure underneath. GPUs for model trainings, and different memory and CPU sizes, and so on. So when we started to think about the platform, we wanted it to be combined of 3 principles. The first one in the left corner is simplicity. Simplicity was one of our main focus areas because we knew that if the platform will be simple enough to users, and we have users with different technical abilities, BI developers, they use SQL code to express their logic. But on the other side, we have developers which are very technology savvy. So we wanted to make it simple to any one of them. So simplicity was one of the main principles we followed by. Monitored, as we wanted to give a higher visibility, a clear visibility of what's happening with our jobs. We defined to ourselves that everything that runs on the platform is going to be heavily monitored. We are going to collect logs, we're going to collect matrices, and on top of that, we're going to base our alerting system. And of course, on the right side, extensibility. I know that simplicity is one thing, but what about advanced users? What about users who want to do things that are a bit more complicated than the normal? So we defined to ourselves that extensibility, extending the platform to developers, is going to be also another principle of ours. Let's talk about simplicity. So how easy it is going to be to take my Python code and to run it every day at 6 a.m. with the new platform. And of course, I'm going to dig into architecture and going to dig into the serverless components right away. But just from the user side, what I have to do if I want to execute my piece of code. The first thing I need to do is to create a folder in a dedicated GitHub repository. As you can see here, it's the DataOps team, which is the team I'm part of, DataOps Bijo. This is the name of the infrastructure. So I create a new folder under job definitions. Into this folder, I put all my code, the SQL code, the Python code, or any other resources I want to use. I need to create a simple and little config file, config YAML file, which inside I need to denote the runtime I want to use. Here is Python. The entry point, I mean the script that we're going to run, and the desired schedule. Here it's 6 a.m. Defined in a cron expression. And after I merge all these files and the config files into the main branch of the cluster, of the repository, Jenkins job will kick in, will take the code, will wrap it, and if something bad happens to my job, I will be notified by Slack that my job has failed, as you can see on the right corner. So from the developer kind of view, all I have to do is to interact with GitHub and Slack, and everything is managed to me. All the underlying infrastructure is hidden. I don't need to take care of where is this code is going to run and how it performs. Everything is monitored for me, and I get notified by Slack. To support this onboarding process of users to create jobs, we heavily documented the infrastructure, as you can see. This is a screenshot from the GitHub page of the infrastructure. We also added a lot of example jobs to users that they can explore the examples and use them as a baseline for their own jobs. And this is what helped users to jump in and use the infrastructure. And of course, as a team, we were standing by them and helping them to onboard and to move their all the BI jobs or Python codes into the infrastructure. Now, you might ask yourself now how everything works, what are we doing underneath? And this is exactly what we're going to see right now. So here above, I have my GitHub repository. Inside the GitHub repository, there's the config YAML file, which I showed you in the previous slides. A Jenkins job will kick in immediately as there is change in the master branch of GitHub. The Jenkins job will take my resources folder and will pack it into a dedicated Docker container that the DataOps team provided to the infrastructure. And then Jenkins will ship that Docker container, Docker image, to an ECR. ECR is a service by AWS in which you can store Docker images, same like a Docker Hub, but on AWS. ECR is extremely scalable. You can store hundreds and thousands of Docker images. You can manage your versions. And of course, you can grab those containers later with another services. So after Jenkins pushed the Docker container, a Docker image into ECR, it will also create a Fargate task for us. Fargate is a service by AWS in which you can orchestrate Docker containers. Let's say you want to have your own Kubernetes cluster. So in a normal setups, you might need to spin up some servers, EC2 servers, to host your Kubernetes servers. and you might need to take care of their CPU memory utilization to scale up, to scale in, and you need to take care of the infrastructure. With Fargate, you don't need to do that. It's a Lambda style thing for containers. All you have to do is to create a task and to tell Fargate, look, I want you to execute this Docker container 5 times for me, and it will pick the infrastructure for us. And since in line number 3, we define the schedule, Jenkins will also create a cron expression for us on CloudWatch, which is CloudWatch Events is also a serverless service that can fire events based on cron expressions, and it will trigger our Docker container in Fargate. Eventually, all the logs, all the std out and std error output will be stored in CloudWatch Logs, which is a service that can manage logs for us from many other services in AWS. By that, basically, we have a very simple yet powerful setup. All the user has to do is to define the config file. Jenkins will take the file, understand which runtime it needs, create the infrastructure and the cron expression, and it will work for the user seamlessly. Now, if I want to add additional packages to my Python code, to my Python runtime, let's say I'm using a specific pandas library, I can do that. We allowed users to use their own requirements txt file in which they can put a lot of different packages, and Jenkins will reveal those packages, will pack those packages into the Docker, and will make them available for the developers in runtime. We also enabled users to customize their Docker infrastructure, memory, and CPU. Let's say I have a memory-intensive job, so I want to tune the default container memory to a different level, so I can do that as well. And another advancement we achieved in the infrastructure is if I'm into SQL, let's say I'm a BI developer, and I don't know how to write SQL code, and I want to express my logic in SQL code, so we enabled users to use a SQL type job, and all they have to do is to provide a config file and a SQL file, and the infrastructure will execute the SQL file in the desired schedule for them without writing any code. That, of course, opened the infrastructure to all the SQL developers in the company, and it made it very simple for them to use the infrastructure. Okay, so it was cool. Yeah, it was cool. People can now go to GitHub. They can push their new jobs every day. They can tune the schedule. They can tune memory and CPU. They can write SQL or Python. They can do everything. But what happens if the Docker container fails for some reason? How can we achieve that monitoring principle we defined to ourselves? In this example, I can see that the Docker container failed. So how can we reveal that? So instead of using a normal way of executing the Docker container, I mean, telling Fargate, look, execute this Docker container for me, we decided to shift a bit, and we used AWS Step Functions. Step Functions is a service by AWS that can help customers define a state machine. Step Functions comes with built-in integrations. One of them is an integration with Fargate. So instead of executing the Docker container directly, we now executing the step function, and the step function executes the Docker container for us. And by that, we now can send notifications directly from the step function to anywhere. And to grab those notifications, we use SNS, which is a notification service. It's a simple service which you can send a message into, and it will fan out all the messages to subscribers. Subscribers might be an email address or an SMS phone number or even a Lambda function. So one side is publishing the event, the other side could be a Lambda function. The Lambda function is triggered by the new event that arrived. So if we combine these two things, we have that now. So a cron expression at 6 a.m. Executes. It tells step functions to execute the Docker container for us. And for some reason, there is a failure. The step function will catch that failure like a big try-catch code section. It will notify SNS if the container failed or succeeded, and the SNS topic will fire a Lambda function, and in turn, it will send a notification to a Slack channel. Okay, so now with that in place, only by adding two simple services, an SNS and a Lambda function, we added a monitoring capability, an alerting capability to our infrastructure. And from the user point of view, it looks like that. We have a dedicated Slack channel for all the notifications, and user get the failure notification, and then they can browse the logs, they can understand what happened to their job. And that was cool, yeah. We started receiving notifications. We had much better visibility into our jobs, and it worked awesome. But then my friend Adi, which is the BI team leader, told me that they want to have some kind of dependencies between jobs. They want to execute job not on a schedule basis, but on a dependency relation to another jobs. Okay, and then we started wonder, and we said, look, we have this kind of setup in place. What can we do in order to support this kind of functionality? How can we create a relationship between two jobs? Let's say I have job A, and if job A finishes successfully, we want to trigger job B. How can we do that? So we did the same trick. We created another Lambda function, which we called job dependency service, job dependency Lambda. Once the step function notified a job finished event, the job dependency Lambda function received that message like the Slack Lambda function. It would check in the database of it if there is dependencies downstream, and if so, it will trigger another step function, and the cycle starts once again. From the developer point of view, all it has to do is to add one more property into the config file and specifying the job he wants to be dependent on. And we took it a bit farther. We allowed users to insert operations between jobs, and we also enabled users to trigger their jobs based on new files arriving or objects arriving to an S3 bucket. So now we ask the question of how this job dependency Lambda can grab the dependency information from the database. How can the database contain the information that the user defined in the config file? So if we take the config file, we use the same Jenkins job that we mentioned before then. The Jenkins will pick up the job depends on definitions. It will send the job definitions to an HTTP service. The HTTP service will send, will trigger the Lambda with the information, and the dependency Lambda will store the information inside the database. So now I introduced you with another service that we added to the infrastructure. It's called API Gateway. And API Gateway is an amazing service by AWS. It allows you to create an HTTP, a REST, or a WebSocket APIs. And you can integrate with API Gateway Lambda functions. This means that you can fire an HTTP request to API Gateway. API Gateway is 24/7 listening to incoming HTTP requests, And as soon as an HTTP request arrives, it will trigger a Lambda function. And you only build for the Lambda function runtime seconds, and not to the API gateway. Of course, you are billed by request, but you don't need to pay 24/7 for a web server to sit back there in your backend. And if you want to do that by yourself, and I encourage you to do that, try to replace your backend services by API gateway and Lambda functions. You can go ahead and open the API gateway console in AWS. Here you can see all the different RESTful resources we defined in our infrastructure. And now I can take the dependency resource, and I can tell API gateway, look, if any HTTP request arrives to the dependency resource, please fire up a Lambda function. Okay, fire up a Lambda function. And by that, we expanded our infrastructure to have an HTTP API in a serverless fashion. Very cool. So after adding the dependency service into our code, we enabled Fundbox to create value. We enabled developers to create value much more easily. So now data engineer could grab data from external sources using an ETL job. And then his job can trigger another downstream BI developer job who takes this raw data and create features. And data scientists can subscribe to the BI developer job and train their models. So we combined users from different teams with different types of technical skills into a single workflow, a single business value to the company. And that was, of course, wonderful. And we are using these capabilities every day in our data organization. So we've been talking about simplicity. You saw how simple it is to create jobs. You saw that Jenkins can grab the job definitions, can pack the resources into Docker container and to execute it. And of course, we also added some monitoring and alerting capabilities using Lambda and Slack integration and so on. But what about extensibility? How can we open this platform to other users who want to take it to the edge, who want to utilize the platform, to utilize the serverless infrastructure with another additional capabilities? So we decided to expand the infrastructure by adding two things. First one is the REST API. Also, we also introduced a Python SDK that wraps the REST API and a custom runtime support. We started receiving requirements for different types of programming languages. I mean, people wanted to write their JavaScript code and to run their Java code or Spark code. So we enabled them to do that. Let's speak a bit about the REST API, what we introduced and how it was implemented in the infrastructure. So we introduced three types of APIs. The first one is the Manager API, which enables users to run jobs on demand. Key Value API, allowing users to store and receive secured parameters such as passwords to databases, intermediate data, and so on. And the Notification API that allows users to send notifications to Slack directly from their code. About the Manager API, to achieve the Manager API, we provide users with a client, a management client, we called it. As you can see, we created a new Visual Tools Python module. Users had to take the management client, create an instance of it, and then run job. And the job will execute as if it was a scheduled job for them. Let's say I have one orchestrating job that executes every day in the morning, and according to some criteria, this job need to run another jobs out there, so it could use the management client SDK and execute another jobs. What you see here is a screenshot from the step functions executions tab. Here you can see all the executions, and you can see that when we fire the execution request from the management client, it will start a new job for us. To create manager Lambda API, we do the same thing, yes? A client sends an HTTP request to an API gateway. API gateway triggers a Lambda, another Lambda, a new Lambda. It's called the job manager Lambda. And the job manager Lambda triggers the step function for us. And again, we're not paying for the API gateway sitting there for the Lambda just over there in AWS. We're paying per request. Lambda is an extremely scalable solution, extremely scalable infrastructure, same as API gateway. API gateway can scale to millions of calls in a minute or in a second. And this integration between API gateway to a Lambda function opened the platform to external requests. About the key value API, so when we had this, and if you recall from the first slides, I showed you that how the user entered the username and the password to the warehouse hard-coded into the Python code. To avoid that, we created a key value store in another service called SSM parameter store, which is the key value-based serverless service that allows users to store key value pairs of information and retrieve them in runtime. So now, instead of doing that, using hard-coded username and passwords, users can now use parameters client, which interacts with the key value parameter store. Here you can see the screenshot from the parameter store. And then instead of hard coding the username and password, they can grab them in runtime from the parameter store. And by that, we made the code much more flexible. Parameters can change over time without even changing the code. And we, of course, increased the security of our jobs. And that was also a very cool feature that we introduced. And all of that thanks to a serverless service called Key Value Parameter Store and SSM Parameter Store by AWS. And I really encourage you to use that as well. About the notifications API we introduced, if you recall, we could send alerts from our Lambda function to a Slack channel. So we decided to open that capability to developers, allowing them to send notifications directly from their code to their team, to their alert channels in Slack. Let's say I'm executing my report every day at 6 a.m. and I discovered that there is some anomaly in the data. So I want to notify my team that something bad is happening or something good is happening. So I can do that. I can create a notification client and send a Slack notification with notification client, and the notification client will integrate with Lambda, will send the information to Slack without me needing to taking care of credentials to Slack, of how to deliver the message, of retries, and so on. So now, if you recall, instead of doing log info the report results, I can now use notification client and send the report results into a dedicated Slack target. Okay, and to do that, we did the same. I'm not going to show you again the architecture because it looks exactly the same. We just added one more Lambda function that coupled with API gateway the notification client sends HTTP request to the API gateway. API gateway in turn triggers a Lambda, and the Lambda sends the notification to the Slack channel. Very, very, very cool. So by introducing the SDK and the Python SDK and the REST API, now advanced users could integrate with our clients. They could send notifications, they can execute jobs on demand, they can read and store parameters on demand. And it was very cool capability. But we also introduced a custom runtime support, as I mentioned before. I mean, as the company grew and we accumulated more and more data, people coming to us saying that they want to write their code, their jobs in different languages other than SQL or other than Python, and to use Spark, for example. And this is why we decided to expand our support for runtimes. To do that, we introduced a new type of job, a Docker job. I mean, instead of providing Python code or SQL code, you could now provide a Docker file. And to do that, you just had to check in your Docker file into the example folder, into the resources folder, to define that the type of the job is a Docker, and to specify the command the Docker container should start with, and everything was executed for you. It was very cool. It opened the infrastructure to other use cases, and people are using that. For example, they wanted to use a slightly different Python runtime. Okay, this enabled them the capability. What about Spark? So when we wanted to add Spark to our code, it was a very, I say, heavy lifting job, as we thought, because spinning up a new Spark cluster requires a lot of things from us. It would definitely requires us to update the cluster, to monitor the cluster. We could use EMR, which is a Hadoop flavor by AWS, but we didn't want to go this way. We wanted to go serverless. We wanted to go with the serverless approach. And to do that, we enabled users to type a new job, a Spark job. We allow them to use Python, PySpark, or Scala, and also enable them to use a different type of workers and different types of a number of workers with a job. And to do that, we used AWS Glue. Glue is an ETL job orchestrator by AWS. It is serverless, fully serverless. Users could use AWS Glue to run their Spark code. It will manage the underlying infrastructure, the Spark workers for them. And this is exactly what to do. Instead of using Fargate to run Docker containers, we now can use AWS Glue to run our Spark code. And this, of course, can run Spark jobs without us needing to take care of the infrastructure below. And that was amazing because it allowed users to use their Spark code directly as it was a Python code, and they now can scale their job to hundreds or I don't know, even thousands in the future workers, rather than using a single Docker container. I think we have not a lot of time left, so I will spare the question. I will have 2 or 3 minutes for questions, but before then, I want to jump over to the end. So we achieved a very simple, as you saw, very monitored capabilities and extensible infrastructure just by using serverless technologies. User now could take their code to push it to the GitHub and to get Slack notifications right away if something bad happens. I know you're not going to run right after the conference and start writing your own infrastructure such as this, but I wanted to give you the broad view of what serverless technologies can do. and I really encourage you to use serverless. It allows us, a team of 4 people, to move very fast, to pay less for infrastructure, and to bring a very good experience to our users. So thank you for that. Thank you for listening. Now I will head over to questions. We have 3 minutes for questions, if you'd like to, of course. Okay. Okay, how big is the latency since generation of alert to received info on Slack? So API Gateway is a very scalable, a very low latency service. I would say, according to our tests, once an HTTP request sent to API Gateway, it takes 100 milliseconds to trigger a Lambda function if it's a cold start. So I would say from the moment the user sent the notification, it takes less than 200 milliseconds to receive notification in Slack. That was the question. Another question is, how long time did it take to develop this infrastructure, and what were the main challenges on the road? So it took us around 3 months to develop the infrastructure. The challenges were first to getting to know the serverless infrastructure and how to combine the things. And I think we did it step by step. We started with a very simple infrastructure, as I showed you in the beginning. We took Docker containers and just tried to execute those Docker containers. And then along the way, we added more and more services and discovered more and more requirements. After all, I would say now we are running with the infrastructure more than a year. We discovered only a single major bug, and all the features were developed extremely fast. Because we used serverless, we don't have to worry about scalability. We don't have to worry about minimizing infrastructure to reduce cost, and it proved itself. So it's about 3 months, and the main challenges were to getting to know the infrastructure, but eventually we managed to do that. If there are more questions, I will be happy to answer them. Okay, I think that's it. So I'm heading over to the Zoom. If anybody else has questions, please join and ask anything. I'm there for you. Thank you for joining me. Don't hesitate to send an email or to send a Twitter message if you want to ask anything, if you want me to help. So thank you, and have a pleasant conference. Bye-bye.